Good evening, everyone. Happy Pythagorean triple square day. I think if I might have said that right, we'll see. I'm sure people might correct me if I'm wrong. Today I'm excited because the date is special, and I don't know if it's coincidental or not, but I think we're going to be looking at some Pythagorean theorem stuff tonight. And so I don't know, maybe this was planned out. Hopefully it was. My name is Mike Houston. I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to get my students excited about all things Pythagorean. With us tonight, we have Karen Camp and Steve Phelps. Karen was instructor of math education at Yale University for 15 years and previously taught high school math as well as middle school math in Connecticut and Pennsylvania. She's been a T-Cube national instructor since 1998, providing professional development at conferences, workshops, and webinars. Karen is passionate about using technology effectively to enhance student understanding in mathematics. Karen, it's great to have you with us.
Mike, I'm so glad to be here, and it was definitely planned for 9/16/25 to have a Pythagorean party.
I'd like to take credit for that, but that wouldn't be right. It was not me. Steve is a longtime geometry, statistics, and computer science teacher, and is currently a math and computer science teacher and math and instructional technology coach for Marymount Schools in Cincinnati. He's a TCube national instructor and also co-author of Advanced Quantitative Reasoning, Mathematics for the World Around Us, as well as the Manna Waits AP Pre-Calculus. So Steve, thanks for joining us tonight.
Thanks, everyone. Glad to be here. I'm looking forward to this.
All right, Steve, what's the plan for tonight?
Awesome. So Karen and I are going to go back and forth, but we'll start out with our welcomes and introductions, which is what's going on now. We'll look at ways to visualize the Pythagorean theorem geometrically and confirm with some area data. I will do some proofs without words. That's my Pythagorean eye candy. Karen and I will both share some triple stuff with lists and spreadsheets, and if time, maybe we'll use a little Python stuff at the end. And as well, if there's time, we will investigate the converse of the Pythagorean theorem. And I'm supposed to instruct you to stay around till the end. There was a number with 3 in it. It could have been 300, but I think it's 3, which is the smallest possible integer in a Pythagorean triple. Would that be correct? And there are going to be 3 things that they give out, prizes that they give out at the end of the webinar. So stick around till the end.
Thanks, Steve. And Karen, what can we expect to be able to do at the end of the webinar?
Once you've gone through the webinar, you can say that I can visualize the Pythagorean theorem using either the TI-84 Cabri Jr. app or TI-Nspire Geometry. You'll say I can enter formulas into TI lists or TI-Nspire spreadsheets. I can use technology animations to prove the Pythagorean theorem, and we'll show you how to access the files from the webinar.
Thanks, Karen. So tonight we're using that chat window. A lot of people have already noticed that by letting us know where they're joining us from. I always think it's fun to just check out some of the people in the chat and just look at how much of a community we have on these Tuesday nights. It's always fun for me to see that. So thanks again for everyone for using that chat window and letting us know where you're joining us from. If you have any questions tonight, Steve and Karen are going to be ever vigilant looking at that chat window. And if there's any questions that pop up, I know they'll try to get those questions answered live. So if you have them, type them in. Also, tonight we're going to be recording this, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. So, Karen, it's all yours.
Excellent. Thanks, Mike. I'm going to share my screen. And I just want to tell you that if you are trying to follow along tonight, you may not be able to keep up with every step, but return to the webinar recording afterwards and try things out on your own or try them out in your class. Where we're going to begin tonight is we're going to begin with the classical Pythagorean theorem demonstration, which is usually, actually, if you go back to what Euclid had in the Elements, the Pythagorean theorem was stated in terms of areas. There were squares on the sides of the legs of the right triangle, and those squares were areas. That's how the ancient Greeks considered areas, and some of those two squares on the legs equaled the square on the hypotenuse. So what we're going to do is I'm going to show you an activity you can do with your students on both the TI-84 and on the TI-Nspire. This is the TI-84 emulator. If you go to apps and go to Cabri Junior, you're going to get into the geometry environment of the TI-84. So what this is, if you had started fresh, you would have a blank screen when you got into Cabri Junior, and the file that we're going to open is in your webinar documents, and it's called Pythag-SQ for Pythag squares. This Pythag 1 and 2 came from an activity that you can download straight from the TI website, but the Pythag square I've added into the webinar documents because it doesn't just have this right triangle and these squares constructed, it also has the areas already measured on the file, on the figure. So depending on your students' needs, you can have students find the area and then work with them. But I like to have this all scaffolded for the students. It makes it a little bit simpler in class. So here we have a right triangle. This right triangle is constructed to be always a right triangle. There's a perpendicular line in there. And in Cabri Junior, it's really easy to use. You move your cursor with your arrow keys to get to an independent point. What's an independent point? It's a point that isn't constrained by the construction. And you can see that this point is sort of flashing at us. And then you hit your alpha key, and that alpha key is going to let you grab and drag. And you can see that no matter how I grab and drag this, that triangle is going to stay a right triangle. Now, the first step I give to all of my students is to grab a vertex and drag, because I don't want all my students looking at the exact same data. But what you can see is that we have the data measured, and you'll notice that 8.1 plus 25 does equal 33.1. When you're done grabbing and dragging, you can hit clear to let go. Hang on, I want to grab it and drag it one more spot. So there are situations where, like this one, the 9.5 and the 29.2 don't seem to actually add up to 38.6. Part of that is a rounding error. Not a rounding error, but the fact that these areas are rounded back to 1 decimal digit. If you hover over a number in Cabri Junior and press the plus button on your calculator, you're going to end up being able to display an additional digit of accuracy. Cabri Junior is sort of a junior size program, so it's only going to give us up to 2 digits. But the most important thing is that the numbers that are in between, that are measured, these area numbers that are measured, they are actually measuring the area to a little bit more accuracy. And so as I'm manipulating this figure, we want students to take down some data into a data table and to show that the sum of the two smaller squares does equal the larger squares. Now, here's the lab activity that's going to be in your file, in your webinar documents, and we're going to have students take down the data for these squares and the sum of the squares, but we don't just want them to write down the area data. We want them to use the built-in calculator of the Cabri Junior in order to get those areas added up exactly. And what I've done for you in this file is I've hidden the sum underneath the word sum. Hit the graph button, which gives us our hide show tool in Cabri Junior. And notice the hide show tool, if you don't know where something's hidden, you won't be able to see it. But I know I hid that sum right over here, and I hit enter to show it. And I'm going to add a digit of accuracy here. And there we have it. The sum of the two smaller squares is indeed the area of the larger square. And this is going to stay true all the way along as I manipulate this. Okay, I'm going to quit out of Cabri Junior for the moment, and I'm going to jump over to TI-Nspire. Oh, there's a fun 3, 4, 5, 9, 16, 25 area diagram that I made for you. But here is the same sum of squares activity on TI-Nspire that we showed you on Cabri Jr. And TI-Nspire is a little bit easier to manipulate. You can use your keypad here to move things over, or since I'm on the computer, I can literally just go over here and grab these 3 vertex points. And it's the same situation. This 90-degree right-angled triangle has been constructed to always stay a right-angled triangle. And the area values are here, and again, they're rounded off. If you want to change the digits of accuracy on TI-Nspire, you use this control menu. Control menu will give you a context menu while you're working on your handheld. And if you're working on your computer, whoops, I got to exit out of all those. If you right click on your computer, you can get to attributes. And so you can change the digits of accuracy here too, if you want more accuracy. But just like the file that I gave you on the TI-84 Cabri Jr., this one also has the sum already done for us. Click here to show and hide the sum, and of course I can add a digit of accuracy here if I desire to. And again, have students drag and observe the sum of the 2 smaller squares equals the area of the largest square. Now, TI-Nspire users will also be aware that there's a way to not just take this data and copy it down onto your lab sheet, but you can also capture the data either manually or automatically. So in the same TI-Nspire file, I have A, B, and C on my, A, B, and C on my right triangle. And these 3 values, you might notice that the A, the B, and the C are actually in bold. That's because I've set them up as variables and I'm capturing the leg values here. Whoops, sorry. I'm capturing the leg values, the A leg and the B leg, and then I'm capturing the hypotenuse values. And so back here on the diagram, when I want to capture a data value, I hit Control decimal point, and then check out that spreadsheet. My data values have been captured, and I set up this spreadsheet to go ahead and square the 2 legs, add them up, square the hypotenuse, and add them up. I can do a few data captures without checking the other spreadsheet. I don't have to switch between pages. And again, this triangle was constructed to always remain a right triangle, meaning I used a perpendicular tool in order to construct it. I didn't just eyeball it. And so now I have a whole spreadsheet here of data. And here, this column here is the sum of the squares of the legs. And this column here is the square of the hypotenuse. And you can see that my data is supporting our Pythagorean theorem. So that is the first activity. Steve, I'm going to send it over to you and share some animations.
I am ready. I am ready. Kids, how are we doing? Do me a favor. Do me a favor. Will you drop like something like a yes or a hello in the chat so we can see what is going on if you guys are with us? So I've got a couple of now look, man, look, this is like eye candy. There are no numbers. There are no numbers. There are just shapes that are going to move around. And I'd love for you to like maybe drop some thoughts in the chat for us about maybe why this might demonstrate the Pythagorean theorem without numbers or words. Now, these first couple are based on Thabit Ibn Qurra. And it was a book that was published, of course, years ago. And these all kind of have the same kind of theme. And this is an Nspire software. When Karen was showing her Inspire software. She was probably in the handheld mode, but I like operating in the computer mode. Just me, kids, just me. And when you have this at, that's a great question, Origin. I do not know, but I can probably find that. When you have this, I have a large kind of a white fat point that I can use to change the size of most things on there or drag the triangles. And there are triangles in here, and there's also a slider here. And so the magic usually occurs when the slider is drawn. So let's drag this puppy. I have no idea what's going to happen. Oh, there goes that one. And there goes that one. And there go. What's going to happen next? You probably know. Hopefully, if things go well, the orange one's going to, and it did. The orange one moved. So when I go back to the beginning, I've got these 4 right triangles. Again, we have to take these proofs without words with kind of like a little bit of faith here that these are all right triangles and they're all congruent to each other. And this larger shape is a square. And what I've done is I've rearranged them. Those 4 triangles kind of leave this white space of two squares. And if I drag this down and rearrange those triangles, they still take up that same larger square area, but now there's only 1 square inside. So think about how that demonstrates the Pythagorean theorem. This next one is kind of in the same kind of boat. And as I drag the slider on this, think about where you see larger right triangles that might be congruent to this right triangle in the middle. But before I go dragging this slider around, I'd like for you to think about how these shapes or how these colored shapes in these squares, how will they end up filling the larger square down at the bottom? So kind of get this in your mind's eye, like where will this yellow triangle move to? Where will this orange quadrilateral move to? Where will the blue and pink triangle move to? And where will this gray quadrilateral move to? So kind of get that in your mind's eye and let's check. And if you got it right, feel free to brag in the chat. So here's the first one. Oh, that was weak. That's not what I thought it was going to do. And I made this thing. That was weak. All right, here we go. There goes that one. So the orange one's going to move next, I believe. Where will the orange one go? Oh, what is the ratio? But that is a good, well, so I think it kind of depends on how this point is set up. So most of these constructions are kind of set up like, oh, there's that one. So these 2 pieces here, the blue one and the orange one, if I did this, these 2 pieces go together to make a right triangle, which would fit perfectly in that right triangle right there. And so I've got 2 pieces left. I think you can see where there's going to go. That pink right triangle at the top, that one, oh man, I wish I could have take a U-turn and filled inside that triangle, but that is the same. And then here goes the gray piece. That goes there. And so there's another one that is a slightly different flavor, but it kind of started the same way. If I drag these pieces up again, there they go. This next one kind of looks the same, almost looks the same in the same kind of set of pieces. But if you could visualize it, I took this white square here at the bottom. If I took this white square and I reflected it or flipped it up over the hypotenuse of the right triangle that is in here, it would seem to like fall naturally over this yellow area and maybe over this light blue triangle area. So if you can visualize that, but once again, see if you can get in your mind's eye where all of these pieces are going to move to. And so here we go. Here we go. Ready? I have no idea. Why do I do the easy piece first? Anyway, they just go straight down. Nice. And so now can you kind of visualize where some of the other pieces are going to go? I think we have some options. And but I don't believe I do any like rotating of pieces, but maybe I do. Let's find out. Okay, that one, that's kind of cool. Look how those two pieces meet. I wonder if they'll always meet that way. Oh. Oh. I could literally do this for the next 30 minutes, though I won't, because that would be almost past my bedtime. So let me drag this. There's a little rotation, and bing, right down there. And then so we've got 3 more pieces left to go. I think I know where the orange one's going to go. The orange one's going to go there. And that orange piece and that dark blue piece would fit in perfectly inside that triangle there, just as this gray triangle and that pink quadrilateral would also fit in there, if, of course, I only move them that way.
So Steve, I think this is just so cool how you can see the a squared plus the b squared, cutting it all up ends up filling the c squared.
Yep. Yep. So this goes back to Euclid's proof, and then I'm going to turn this back over to Karen. But the Euclid's proof is kind of classic, and if you stay around to the end, there's another one at the very end that is a generalization of this. But you've got to convince yourself that no matter how these shapes are changed, I'm going to shear the shapes. I'm going to shear, which is like slide the tops over, but leave the bottoms kind of attached. So I'm going to move these 2 squares like this. And they go right to there. Question for you in the chat if you want to drop this down. If you want to think about this, the distance from that vertex of the triangle up to that point, from that point all the way up to that point, I claim that length is also the hypotenuse. The length of the hypotenuse, that's what I say. But also, how can you convince your students that those areas did not change? So those 2 squares there and those 2 parallelograms still have the same areas as they did originally. I'm going to shear them again by doing this. And then slide them down neatly into the square. And that would be kind of an example of Euclid's proof. There's probably a bride's chair that should be in here somewhere, but I took that out. But anyway, that is Euclid's proof, and there's a couple of the things that you have seen, some visual kind of proofs without numbers, proofs without words, and they're not proofs, they're merely demonstrations, but you can argue why they are true and how they kind of convince you that the Pythagorean theorem might be true. But we'll see some other ones after we share some spreadsheet stuff. So Karen, I'm going to stop and I'm going to hand it back to you.
Super. I want to make a comment, actually, about the Cabri Junior files that I was sharing before. So some of you are in classrooms that have a mix of TI-84 models. Some of you have the grayscale models. There is a Cabri Junior on the grayscale model, but it has, since the screens of those grayscale models has a different number of pixels, the files don't work on the same files won't work on the grayscale 84 as they will on the 84 color CE. But you can do some of these same things on the old grayscale, but they're not going to be able to use the files that I'm sharing tonight. Okay, so Steve ended with the Euclid algorithm and or the Euclid proof, and what we're going to look at now is we're going to take a look at the a Pythagorean triple generator. And the Pythagorean triple generator is that I'm going to be sharing with you is Euclid's formula, where you have to choose 2 numbers, m and n, where m is larger than n. Then our a, b, and c for the 3 sides of a triangle. The a value is m squared minus n squared. The B value is 2 times m times n, and the C value is m squared plus n squared. So we're going to take a look at this again. If we have time, I'm going to do it on both platforms, but let's get to the TI-84. And you might be saying, Karen, there's no spreadsheet on the TI-84. And that's true. We do have the stat list editor. Table of values that you can see using a function in the y equals is something different. These list editors usually are just to put in some data, scatter plot kind of data, but we're going to use them to create our Pythagorean triple generator. And I'm going to begin with the number 2 in list 1, and that's going to be my m value, the first value of the generator. What I want to show you tonight is how we can use a defined formula, otherwise known as a locked list, so that this will act like a spreadsheet. If you arrow up to the top of a list and press enter, your cursor comes down here at the bottom and it gives you the opportunity to type something for the list. And what we're going to type is I want to take the value of L1 and subtract 1 away from it. It's not the only way to ensure that m is bigger than n, but it's one way to do it. Now, normally I could just do second 1 to get L1 and subtract 1. But what's going to happen if I do this? It will subtract the value for any data that is already in L1, but it won't be an active formula to always work. And so in order to make this an active formula, what I want to put in here is I want to put in a quotation mark. So I could have started with this. I need to do alpha plus symbol to get that quotation. And by putting this quotation marks around my formula, I am going to make that formula a dynamic formula defining this list. When I press enter, if you notice, it does the computation, but it also puts a lock symbol at the top of list 2. Okay, I'm going to carry on to the top of list 3. List 1 is my m value, list 2 is my n value, and list 3 is going to be my a value. Press enter, get my quotations, and my a value is going to be L1 squared minus L2 squared. And then I close my quotations. Whoops, it did not like that. What did that not like? Okay, let's see. Okay, I do not know what it did. Okay, this is one of the error messages that I was trying to avoid, but what I can tell you is that I'm not sure why this happened. Oh, I see what's the problem. I am trying to enter this into L3 box 1, so I need to clear this. I need to go up to the top. So same thing as before, but I put it in the wrong place. Now I'm defining the entire list. L1 squared minus L2 squared. And I'm going to do for L4, enter. I'm going to do 2 times L1 times L2. And finally, for L5, I am going to do L1 squared plus L2 squared. Now, if you don't like a situation where students are watching you and you're worried about making a mistake and you want to load this up in advance, within the SmartView emulator, you can save an emulator state. And I'm just going to show you up here under actions in the actions menu. I actually set this up earlier and saved the emulator state of the calculator so that if something had gone wrong just now, which it did, but if I didn't want to redo it, I could load the previously saved emulator state to make sure that things are going to work the way you want to. And the way I usually use this in class is the bell's about to ring, so I save the emulator where my 5th period class was, and then the next day I can load it back up. Anyway, here we have our list, And you'll notice that we have 3, 4, and 5 as our first triple. If I change or add another data point into L1, I get another triple, 5, 12, 13. 4 gives us 7, 24, 25, and so on. And we can see a whole bunch of Pythagorean triples generated. Now, this set of list of triples that I'm generating, you'll notice that the m value is always one more than the n value. You can do it with other arrangements. You might not get a primitive Pythagorean triple, but you might get a multiple of a Pythagorean triple. Now, I will tell you that these locked lists can be kind of tricky. And so when you're trying to clear them out, you don't want to clear your L1 column because all the other lists are defined based on this. And so when you are done with what you are doing, you're going to want to, actually, let me just go back there for a second. Let me take a screenshot so we have this for ourselves. Okay, and now going back to the home screen, if you want to clear out those lists and not worry about error messages, go to your catalog, hit the letter C to get down to the C's, and the command you want to get that stuff out of your lists is clear all lists, and that's going to clear everything out without you ending up with a definition problem. Now, I'm going to send it over to Steve to show you a different kind of generator, but that same generator that I did, you can do on TI-Nspire. And Steve, when you open up your generator, will you just show them where the formula line is for the Euclid's formula if they wanted to just replicate what I did on the TI-Nspire?
Yep.
Okay, all yours.
So I think one thing, kids, one thing I did not mention before is that these make wonderful things to 3D print. So if you can make them a little bit thicker, a couple years ago, before in my current position, I worked with a number of elementary schools around town, and I would make these puzzles for teachers and their kids, and they loved them, and it would keep the kids busy. Can you arrange these pieces into 2 squares? Can you arrange them into 1 square? And so they're doing Pythagorean theorem in elementary school and didn't even know they're doing Pythagorean theorem in elementary school. So I am, so this is mind blowing, man. I've been thinking about this. I shared this with our geometry teacher today. And in my spreadsheet, if you were going to create like a locked list formula sheet, I would use this row. The top row is where the columns are, and I've named the first one Fib, short for Fibonacci. And then the other ones I did not label, so I could refer to them by their column letter, B, C, or D. And then right below those is where I could write down formulas if I wanted to.
Right, so that right where Steve's cursor is, if you wanted to put in the formulas that we had that I was showing you, you would put them right in here. And honestly, what's great about the TI-Nspire, it's not limited to one input like the TI-84 lists are. You really only can use one input. Here you can use multiple lists for your inputs.
Now, I did mine more like a regular spreadsheet, which is what I think the power is of this. And if there's one takeaway you can take about spreadsheets today, is I honestly believe that spreadsheets are the gateway drug to computer science. So if you can get your kids working with spreadsheets, one day they'll commit their life to computer science, and there you go. Everything's going to be better. So here we go. So I started out with Fibonacci. So I started out with 1 and 1 in that first 2 columns. And then you can see at the bottom of the screen, I generated this third number in A3 by just taking A1 and adding A2. And then I filled that down. So that was a relative fill in a spreadsheet. And so I will go up here to this row. And if I go over to, now I'm looking at that, 39, 80, 89. I hope that's a triple, kids. But if I go over to that first cell, that B4, and that is A4 times A7. So it is this number times that number. So if you take any 4 consecutive Fibonacci numbers can be combined in this way to get a triple. So the first number in the triple is the first Fibonacci, and the third one after it. So 3 times 13 is 39. The second number in the triple is the middle two numbers multiplied together and doubled. So 5 times 8 is 40, double that puppy, 80. That one's 80, and that's what I have down there at the bottom. I have 2 times A5 times A6. And then the last one almost feels like cheating. It is the middle two, the sum of the middle two Fibonacci numbers, the consecutive ones, squared, the sum of those two squared. And that gives you your hypotenuse, if you will. So any 4 consecutive Fibonacci numbers can be merged together in that way, where the first one is the product of the first and the fourth. The second one is twice the product of the two middle numbers. And the last one is the sum of the squares of the two middle numbers. And that is how I can get triples from Fibonacci numbers using the spreadsheet on the TI-Nspire.
And those formulas are on our slides that are in your webinar documents if you didn't catch it. And yes, Steve, 39 squared plus 80 squared equals 89 squared.
But again, when I did not mean to do that one here. What about these? Will someone confirm this one? Will someone confirm 229,971, 459,940, and 514,229? Is that a triple? What if we found one that
Yes,
wasn't?
it is.
Oh man, there.
I did it right on my 84.
There we go. Okay, so these next couple are Parago's proof, and these are kind of some themes along these lines, and I kind of like this one. So there is no triangle here. I can drag this. I can kind of change these shapes here. I've got 2 triangles. I debated whether or not 2 triangles, 2 squares. That was a teacher technique. Mike Houston knows what a teacher technique is. So these are 2 squares, and I debated putting this little smaller square on the outside, but I think it might make things easier to see. But there isn't a triangle. But as I drag the slider around, I can rearrange these pieces. Instead of being in 2 squares, I can arrange them into one larger square.
Ooh, so cool.
It would be super cool if I could kind of visualize where a right triangle would be. But if I go back to my original setting, these diagonal kind of cuts or creases through the center of that square would be the hypotenuse of a right triangle. So you could almost visualize if the polygon, the little word polygon would just quit blinking at me. That diagonal line through the center, that is sort of the hypotenuse of the triangle that is missing. And as I mentioned before, this is a wonderful thing to 3D print and give to younger kids. I can make can I arrange these 4 pieces into a square? Yes, you can. So these next couple are kind of similar theme. This is what you might see in in more of a Pythagorean theorem field, but it's almost exactly the same proof. Now, I want you to get in your head here. Think about where these colored tiles down here in the bottom will move to into that square on the hypotenuse. Kind of commit that into your mind's eye and kind of commit to something, and we'll drag them slowly. Where will the blue one go? There it goes. It goes there. And so now we can figure out maybe where the other ones will go. It's almost like these little corners here, which are right angles, must end up somewhere at one of the other right angles. And this construction, if you were wanting to construct this yourself, and again, I wish we could take time to show you how these work. And I can certainly show you, if you reach out to me afterwards, I'd be more than happy to sit down with you on a Zoom and show you how to do this. These cuts down here, that kind of that cut that's going this way is parallel to the hypotenuse. And this cut that goes down that way is parallel to these sides of the square. So an interesting little kind of a way to make that construction. This is the same kind of construction as the previous one, just upside down. And instead of the lines going through the center of the square at an angle, they almost look like they're perpendicular or parallel to the hypotenuse. But get in your mind's eye, where do you think these pieces will move to when I slide that slider? So where will this yellow piece go? Where will the blue piece go? Where will the orange piece go? And where will the pink piece go? And so here we go. And that kind of, it will go there. And so now I think you can see where the blue piece goes there. That's not what I expected, but I was thinking it might go up here. Pink one's probably going to go right down here. Oh my goodness gracious. It goes right there. There's the orange one. And so then the pink one will end up here. And the square goes there. And these cuts between all the pieces down here on that square and the hypotenuse are either parallel or perpendicular to the legs of the right triangle, depending on how you look at it and your point of view. But again, this is another good thing to 3D print. If you have access to a 3D printer, and they don't need to be thick, they don't need to be maybe 1/8 of an inch thick, but they make great puzzle pieces for younger students. Now, this is a nice one. I had seen these around and started to make them, and it's surprisingly, this construction was surprisingly easier than I thought it was going to be. It is on that Paragul's theme, but I'm going to pivot these pieces in place. So this is, and you can't do this on TikTok because they'll accuse you of other things. But anyway, that is that. So I'm pivoting those pieces literally around, kind of around a center of each of those quadrilaterals. So I've taken these 4 pieces, which are fitting into a square, and by rotating them around in place, they are rearranged to form another square with a small square in the middle. And similarly,
So that's like c squared minus b squared equals the a squared.
yeah, wrong one, but yes. I've taken the 2 areas and put them together, and I can remove that one. I end up with the smaller square. And this is similar to the other triangle proof we saw. If I can change these shapes a little bit, I will pivot those pieces around in place. And these 4 pieces fit nicely into a square. And I can turn those pieces around. And there is my larger square with a smaller square inside. These are all great puzzle pieces to make in 3D printing. If you like 3D printing and want some other ones, these are some nice ones here. These are attributed to Botker, and they have like similar kinds of themes. And so can you get into your mind's eye where these pieces are going to go? How they would be rearranged. So where will this yellow piece go and where will that orange piece go, for example? And so let's see. Well, I started out with the easy one. There's the orange one. They slide straight down. So I think you have an idea where that orange or the yellow one might go. That's what I was thinking. So now where will the pink and green one go? Oh, I did not expect that. That's not what I expected. Yes, I agree. This would be this is another one that is a nice puzzle piece, and it would keep kids very busy, and you could lay these in 2 different ways. So there's that piece to it as well. Would be super hard for a younger student, but for your high school students, it would also be good. There are a couple of versions of this next one that are based on X circles and N circles. And I have a construction of one that's based on the X-Scribe circles that I have not seen before, but this is another one that is also good for 3D printing. Can you visualize where all of these pieces are going to go? And the big squares, this almost takes me back to that first one I showed you where we started with two squares arranged this way in a larger square, and these other pieces were filled with two right triangles. But I don't know how we're going to get two right triangles in each of those pieces out of this. So let's see where these pieces go. There's that one, and that one, and that one, and that one. And so now we have the rest of those pieces that fit like that. This is another good 3D printed one. Now, another fun thing to do with these are hinge dissections. And hinge dissections, it's just best to show you again. You've got 8 pieces, and each one is sort of attached to a neighbor. And this is your hinge. I've got these arranged in a square, and they can be hinged and moved and rearranged into a larger square that encloses a smaller square. So similar to some of the other ones that we had before. And the Pythagorean theorem is certainly more than just squares. Hinged triangles work the same way. Any polygon can be hinged. But I think this is probably my favorite generalization of the Pythagorean theorem. And this is attributed to Apophis of Alexandria. And the triangle doesn't need to be a right triangle. So I can have any triangle, and I can have any parallelogram on that longer side, and I can have any parallelogram on each of the two shorter sides, and they're not similar to each other. They are not similar to each other, but they are connected to each other. So let's see how these are connected, and let's see if we can fill this large parallelogram down here with versions of these two parallelograms that have the same area. So I'm going to, that's a little shear. I did a shear like we did before in Euclid's proof. There is a shear, so that area has not changed. And here is, I shear it down and I slide it in. So there you go. And then this one is going to go the same way. I shear it up. And it does turn out that this length here, if I would have done this differently, I should have thought of that. When I sheared the yellow one, they meet at that same point up there. So it's very similar to that other proof. And I can shear it down this way, and then I can shear it a little further. And the secret is that length up there, where those two pieces kind of sheared to, is the same as that length, which is parallel to the sides of this parallelogram. So it's kind of like the height, the slant height of that parallelogram on the hypotenuse. And this does not need to be a right triangle. And it's a version of the Pythagorean theorem, a generalization, but it does not need to be right. But if it was right, then we could possibly arrange these pieces into squares, but I'm not going to do that now. Again, I included in some of the workshop files a Pythagorean theorem program, which makes a lot of triples. It's kind of cool, but I'm not going to show that now because Karen's got one more cool thing to show you about the converse of the Pythagorean theorem. Then make sure you stick around because Mike's going to give away 300. No, three, not 300. 3 gifts at the end. So thanks, kids. I'm turning this back over to Karen.
Okay, so what we're going to do, there we go. Now I'm unmuted. Okay, so what Steve was last showing, that generalization without it being a right triangle, I think that if we actually messed around with the areas there, I don't know that the areas were actually the square areas, because the converse of the Pythagorean theorem says if c squared equals a squared plus b squared, then we have a right triangle. But if c squared is greater or smaller than a squared, we have a different kind of triangle. So let's go back into our Cabri Jr. And I just love doing lab activities with my kids. I love for them to investigate, gather data, and decide for themselves what works. So let's see. So the activity here is called Pythlab, Pythlab, and this one is, I've already done some of the work on this. This is a generalized triangle, and this 82 degrees at the top is the size of that angle up at the top. You'll notice that this triangle is an acute triangle, and the key thing you have to watch out for is that whatever side is the longest side is the one that you need to call C. And so the way I've done this, I've had that 12.0 side as my C, but you got to be careful. Right now, I've got C squared is less than a squared plus b squared in my acute triangle. If I make this move in a way, wait, that's not going to work. Let's see. If I change this so that the 12 at the bottom, my C at the bottom, is not the biggest. Here, watch this. I'm still an acute triangle, but now my bottom segment is not the smallest. And you can see that no longer, it may not work out properly. Actually, this one still works out that a squared plus b squared is bigger than c squared, but that's an artifact. So the bottom line about using these is make sure that whatever you're calling your c squared, that's going to be the biggest. So here is c squared is smaller than a squared plus b squared. If I keep going, whoops, that's still making me an acute triangle. If I go down, look, I've got a 90-degree angle. This is a little bit of rounding error, but if this was exact, c squared would equal a squared plus b squared. And now as I go into an obtuse triangle, c squared is bigger than a squared plus b squared. So that is the Cabri Jr. version. Here is the lab activity where the kids are identifying what type of triangle they have. They're giving the three sides of the triangle, finding the sum of the squares and c squared, and they're deciding under what conditions will c squared be greater than the sum, c squared less than the sum, and does the right triangles confirm it? And then I ask kids to apply the math and make a prediction. And look at my last question. I threw this in there because one year I had kids creating a set of sides that would make an obtuse triangle, so they just made C really big. And I realized that some of them were forgetting about the triangle inequality theorem. So I encourage you to put into your lab activities other thinking questions that kids need to think about. Back on the TI-Nspire side of life, I've got the same figure. Again, I can show or not show the data, a squared plus b squared. Whoops, here we go. If I make an obtuse triangle, then c squared is bigger than a squared plus b squared. If I make an acute triangle, c squared is less than a squared plus b squared. And I don't know that I'm going to get exactly a right triangle, but we can try. That's pretty close, not exactly. But that's the converse of the Pythagorean theorem, that lab activity. And this was actually one of the first things I did with Cabri Jr. geometry and Inspired geometry. This is one of my favorite activities to have kids do. Okay, I think that Steve, do you want to show that Python generator just real quick? Because I think we still have a couple more minutes before Mike needs to wrap up this Pythagorean party.
Okay. I will share and again, eye candy, a lot of cool patterns involved, a lot of cool patterns. So here is my, I just plotted all the points in the first quadrant that were the, like the A and B in A squared plus B squared equals C squared. And this is the larger one, very hard to see. What I did is I ran this 4 different times with different loop structures on them. It is, I wonder if it would look better if I did computer mode. Nope, I meant handheld mode. That was a teacher technique. There's a little bit better view of it where you can see some of those curves and a lot of the patterns. And I was showing a version, something like this. We have a group of Algebra 2 kids who are in 8th grade, and they were doing some math counts problems, so I showed them this the other day. So this is one of the things that you will get also in the files if you're a Python user. Play with this, but that's all I got, kids.
All right. Well, it's time to
Mike,
wrap.
before you do the things, I just want to say not only this is a Pythagorean party, but we want to say happy birthday to our friends Fred and Dana, whose birthdays are today.
Thanks so much. All right, on to our not 300 but 3 prize giveaway. Normally it's just 1, so this is a
I was just
special night.
unsure. I was unsure. I heard 3, but then
Yeah,
not feeling well.
wishful thinking, right? So our first winner for the graphing calculator of your choice is Denise Van Horn. So congrats, Denise, on that. The plushie is Amy Wilcoxon. Hopefully I said that right. And for the swag bag, it is Demetrius Miller. So congrats to all 3 of you. I'll be reaching out soon to get some information from you. But congrats, and hope it was worth everything you got tonight. Speaking of getting things, to receive a certificate of attendance as well as a link for the documents, which I know that a lot of you are waiting for those documents, go ahead and click the link in the chat window. Also listed, so there's 2 links there, one for the certificate, one for the documents. And if any of these aren't working for any reason, just hang tight. You're automatically going to get a follow-up email in a couple days. And that follow-up email gets you the same thing. It gets you the link for the certificate, a link for the documents, but it also gets you a link to watch this again. So you can watch it a little bit slower and at your own pace. And if you're watching this on demand, copy that link into your favorite browser to receive your certificate. Feel free to give us a call or send us a text. I don't know what I'm doing tonight. Give us a call or send us an email at ti-cares@ti.com. If you have any questions about anything that you saw tonight or anything in the future, let us know. We'd love to help you out. When you leave this webinar tonight, the party doesn't have to stop. You'll get a couple more questions and a follow-up survey. Let us know what you think went well and if there's anything that we can improve on, and specifically, if there's anything you want to see in the future. We'd love to hear from you. So huge thanks to Karen and Steve for all the fun that you guys shared tonight. It definitely was. Well, I learned some things, and I thought I knew a lot. So it's always awesome for me whenever I learn something. So thanks for everything.
Thank you for coming to our Pythagorean party. You can find me on social media at Karen Camp, and you can find Steve at Math Tech Coach.
All right. Well, thanks again, everyone, and we hope to see you back online next week. Let me take a quick look. I should already have known this. Next week, I think we're going to focus on the SAT and unlocking some SAT potential and using TI technology to do that. So come check us out next week. And let me see if I can.
Wait, Mike, one more thing. I just remembered. If you're on Facebook, look for the TI Educators group. There's a group of us there, and you can also ask questions and get resources there as well.
Thanks so much, everyone. And again, we hope to see you back online real soon. Have a great night.
Night, guys.